first. See if everything works. Somehow your screen is a little narrow. It's like takes only one part of the screen. Can you?
Yeah, I guess
Yeah,
I can transpose it.
All right.
Do I see Tyler in the background?
Yeah.
Yes, hello.
Tyler.
Hey,
How are you?
pretty good. How are you?
This way, it doesn't show Tyler. We have this wonderful meeting owl, which follows the voice and kind of turns its head automatically towards this person who speaks.
Ah,
So,
very nice.
So this is Tyler. Hey, Jonathan?
I am.
Yeah, I'm Sasha Williams.
Nice to meet you.
We should chat for a second. Sure. All right, David is here. Okay, very good. Yeah, so actually, I think we are ready to start the talk. The talk is supposed to go for 50 minutes. In a little bit over an hour, I have to teach, and we'll have to start the session. But today we have a pleasure to have Achim Krause delivering the second part of the mini series, which was wonderfully started by Ben Antio a week ago. And so Achim will be talking about the K-theory of Z over P to the nth, and that's part 2. Please.
Right. Yeah. Thanks for the invitation. It's a pleasure to speak.
Sure.
Yeah, as you said, I will be talking about this project with Ben Antio. This is joined with Ben Antio and Thomas Nikolaus, where we compute the K-theory of Z mod P to the n, and actually a little bit more general rings than that. And the way we do this, let me recap very quickly what Ben told you last week. So the way we do is we compute the K-theory of rings of the form OK mod pi to the n through trace methods, i.e. through comparing with TC. And OK mod pi to the n here, I mean K is some finite extension of QP, the p-adic rationals, and then OK is its ring of integers, so everything of non-negative valuation, and pi is some uniformizer. So you can think here of something like ZP mod P to the n, but more generally, you could also take something like ZP adjoint some root of P or some root of unity or something like that, and then mod by a power of the uniformizer there. And that's the generality that we're working. And it turns out the trace methods approach works very well here, namely TC just agrees with the P completion of K theory, at least in non-negative degrees. And so it turns out that's the only interesting part. All of these are finite abelian groups, and the non-P torsion part is easy to understand by Gabor rigidity. Right. So we want to compute TC, and the classical way of approaching this is, right, if you remember, TC is one of these refinements of THH. So the classical way, the way this was first done is you start with computing THH and then something like TR, which is another refinement, and then TC. And there's more modern ways that go through computing like TC minus and TP, which are yet other refinements. There's certain kinds of fixed points on THH. and then to go to TC from there. And the key ingredient that we bring to these computations is there's a kind of shortcut you can take nowadays, which is usually the way to understand these things is in terms of spectral sequences. So you start computing THH, you get some description there, then you have to apply another spectral sequence to get something that gives you TP or TC minus, and you usually lose some control over how canonically you can describe elements and so on. And the shortcut that you can take nowadays is you can describe these in terms of prismatic cohomology. So that's the main thing we're doing. And in fact, once you've set up the relationship between TC and prismatic cohomology, you could say that the rest of the things we're doing is actually more algebra than proper homotopy theory. So what's the relationship that I'm talking about? Well, this goes back to work of Butt, Morrow, and Scholze. So it turns out that on all these spectra, there's a filtration. So there is a Butt, Morrow, Scholze filtration on TC minus, TP, and TC, and the associated graded admits descriptions in terms of prismatic cohomology. So let me write that out maybe for TP. So for TP, you have that the ith associated graded admits a description like this, where this here, I'll explain later what that means precisely, but this is the symbol for prismatic cohomology of the ring R. And then there's a certain twist appearing, the Broyle-Kissin twist, and everything is shifted to degree 2i. So the way this works for certain very nice rings, namely perfectoid, or more generally quasi-regular semi-perfectoid rings, is that TP will actually be completely concentrated in even degrees. And in that case, this filtration will really be the Postnikov filtration. And so the individual pieces will really just be the homotopy groups. So you could think of prismatic cohomology as somehow being something like an algebraic description of the homotopy groups of TP through some nice algebraic universal property. But of course, in general, for more nasty rings, this is not going to be true that these are going to be concentrated in single degrees. And in fact, this is one of those rings, right? So stuff like Z mod P to the n will not have prismatic cohomology concentrated in a single degree. Right. And well, for TC minus and TC, there are similar descriptions, which maybe I'll talk about later. But so that's the goal. We want some explicit handle on prismatic cohomology of rings such as Z mod P to the n. And the strategy is we approach prismatic cohomology of these rings R through relative prismatic cohomology, where we work relative some power series ring, ZP adjoint Z. And this is inspired both by previous work that Thomas and I did, where we explain how to get absolute THH from relative THH, where you work relative to some polynomial algebra over the sphere, and also a paper by Liu and Wang, where they compute TC of ZP, but mod P, by a similar way where you descend from the relative case. And we're basically carrying out that strategy, but completely on the side of algebra in this world of prismatic cohomology. And let me maybe right away state the type of results we're getting before I explain to you what the hell this prismatic cohomology stuff is about. So concretely, what we get is that for rings such as this OK mod pi to the n, and for any I, we get a square consisting of free ZP modules, all of the same finite degree. So the degree is f times in minus 1, where I is the number here, n is here, and f is the degree of the residue field of OK. So in this case, z mod p to the n, that's just 1. So in that case, just ignore f. So we have a square like this and an identification of the cohomology groups of the total complex of that square. So think of this as a bicomplex, and now take the total cochain complex. This is a 3-term chain cochain complex. So the claim is H0 is just 0. So in other words, these maps here are jointly injective. Then the degree 1 cohomology is k 2i minus 1 of r, and the degree 2 cohomology is k 2i minus 2 of r. Right? So, and the key point here is that these are not just some abstract, this is not just some abstract existence result. We really have a description for bases of all these guys here, and a description for how these matrices look like. And as Ben told you last week, we can actually program that and get explicit tables for K groups through some range. And that's all nice and well, but we can also use this to prove some actual patterns that work for all degrees. So we can also show what we call the even vanishing theorem, which is that for large I, depending on your ring R, and we have explicit bounds, the even K groups are actually 0. So this is saying that for large I, these maps here somehow become jointly surjective. And as a consequence, we also get explicit formulas for the orders of the corresponding odd group. Right. The way these are related to each other, and also the way that somehow for every I we get a single square that gives two adjacent K groups, is that this BMS filtration here on TC, remember we're comparing TC and K theory, on TC the BMS filtration actually turns out, well, I mean, the graded has some description in terms of prismatic homology, and this turns out to be concentrated in only 2 adjacent degrees. So what this square is actually computing is it's computing the ith associated graded of TC under the BMS filtration, and that happens to be concentrated in just 2 adjacent degrees, and so the usually you would expect a spectral sequence that tells you the true homotopy groups of TC from whatever you compute for this associated graded. But in this case, this all degenerates, and you can really read off the homotopy groups. This is one of the reasons why we have to focus on rings like this. I can say something about larger generality in the end, maybe. Right. So now what I want to do is I want to give you some feeling for what this prismatic cohomology stuff actually looks like, and maybe in the end give you some feeling for why this happens. So we talk about prisms and prismatic cohomology. So the key ingredient in the definition of prismatic cohomology is the notion of a delta ring. Let me tell you what that is. So a delta ring is a p-complete commutative ring A with a map delta from A to A such that delta of x plus y is delta of x plus delta of y plus x to the p plus y to the p minus x plus y to the p divided by p. So this is saying that delta is somehow, it's definitely not additive, but it somehow plays well with sums. And there's a similar relationship between delta and products, which looks maybe a little bit like delta being a derivation. Just that it's not a derivation over the identity morphism or homomorphism. It's somehow a derivation with this to the p, and there's this additional term here. And this looks really weird, but there's actually a reason for why we're asking exactly for this. Namely, these rules here are chosen exactly in the way that if you define a map phi on A as x to the p plus p times delta x, then this is a ring homomorphism. If you write out what it would mean for this to be additive, then you would basically need exactly this, or rather p times this. And if you would spell out what it would mean for phi to be multiplicative, you would get basically p times this. So in fact, another way of saying what this is, it's a lift of the Frobenius that you always have from A to A mod P, right? A itself might, of course, not be a characteristic P, but you always have a Frobenius homomorphism down to A mod P that really takes x to the P. And of course, if you have a lift of that, then phi of x must be somehow congruent to x to the P mod P. And from this train of thought, you can actually prove that on a torsion-free ring, a delta structure is the same as a choice of lift of Frobenius. So somehow delta structures are the replacement for just a ring with a Frobenius lift in the presence of p torsion. And here are some important examples for us. One is ZP with Frobenius lift given by the identity. And if you spell out what that would mean for the delta to be, well, then delta x needs to be x minus x to the p divided by p. More generally, generalizing from this example, you can also take something like Witt vectors of some perfect field or perfect FP algebra with Frobenius lift given by the Witt vector Frobenius. And similarly, you can work back what it would mean for what delta is. It's again Frobenius minus x to the p divided by p. And then finally, this is going to be important for us. You can put a delta ring structure on a power series algebra where we just ask for the Frobenius lift to just take z to the p. And it's equivalent to asking that delta just kills z. Right. So that's what a delta ring is. It's basically just a ring with Frobenius lift, but we encode that in terms of this p derivation, this delta. Now, what's a prism? A prism, and let me first tell you what an oriented prism is. So an oriented prism, A, is a delta ring such that, a delta ring together with a choice of distinguished element. D in A. And so what does distinguished mean? Distinguished means two things. First of all, A is D complete. So it needs to be complete not just with respect to P, but also with respect to D. And the other thing, that's the more important thing, is that delta D is a unit. And then a general prism is a pair of a delta ring A and an ideal I, such that I is Zariski locally generated by a distinguished element. So basically, you're just not remembering a choice of distinguished element, just the principal ideal generated by it. And maybe for this to be very well behaved, you want also that D is a non-zero divisor. But that's going to be given in all of our examples. So again, let me look at examples. Well, first of all, we had this nice delta ring ZP with the identity before. And there's a nice choice of distinguished element in there, namely the element P. So my prism is ZP with choice of P. Sorry, with the ideal generated by P as the choice of ideal. And why does that work? Well, recall that delta P is something like P minus P to the P over P, which is which is this guy. And of course, in the p-adics, that's a unit. So this is a distinguished element. Generally, what's happening if you apply delta is that somehow things become less divisible by p. The valuation drops by 1. So somehow other distinguished elements in here are given precisely by multiples of p. So what's a little more interesting is this other example, this ZP adjoint Z. Basically, what I've just told you is there's only one choice you can make for the ideal on ZP. Turns out here there are many different choices you can make. And they basically correspond to choices of Eisenstein polynomials, at least up to unit multiples. So let's see that works. Let EZ be some Eisenstein polynomial. Then what is delta of EZ? Well, again, you need to apply the Frobenius, which in this case just substitutes Z by Z to the P. And you need to raise EZ to the pth power, compute the difference, divide by P. And now, whatever this is, it's mod Z equal to E0 minus E0 to the P over P. So again, if E0 is some unit multiple of P, as is like that's one of the conditions for being an Eisenstein polynomial, then again, this is a unit. And since we're complete with respect to Z, that implies that this is a unit as well. Right? So that gives us a huge list of prisms, basically one for each of these OKs. Just pick the corresponding Eisenstein polynomial. These are different prism structures on ZP adjoint Z. Okay. So what is prismatic cohomology? So prismatic cohomology comes in two flavors. There's a relative prismatic cohomology and absolute prismatic cohomology. So let me first tell you about the relative prismatic cohomology. So there, the input data is somehow a prism. Prism A, and a ring R, which is an A mod I algebra. Right? Remember, a prism comes with an ideal. And then the prismatic cohomology, which I'm going to write as prism R relative A, is going to be a limit. And it's going to be a limit over the relative prismatic site of R. So how does that look like? Well, remember, So I have my prism A, and this comes with a map down to A mod I, and this maps further to R. And now objects in this relative prismatic site are just given by a prism B, which again comes with some ideal. And then I want a map from A to B, which is a map of prisms. So it needs to be a map of delta rings that takes the ideal to the ideal. And downstairs, I just want a map of rings. And what I take the limit over here is I take the limit over B, right? So I have this kind of under category where objects are prisms, where I have a map of A to B and a map from R to B mod J, and the square needs to commute. Then I take the limit over B here. So in this simplest example of ZP with the ideal given by P, your input datum here would be some FP algebra, right? A mod I would be FP. And what you're doing in effect is that you're somehow taking a limit over, so to say, all possible ways to lift R to characteristic 0. So, and of course, there's this delta structure in the mix, so it's not literally all possible ways to lift R to characteristic 0, but it turns out that if you do it this way, it behaves well. For example, in this case where A is ZP with prism structure given by P, this prismatic cohomology can be identified with crystalline cohomology. So, but this generally, I think what you should remember of this is that it somehow lifts stuff, right? You plug in an A mod I algebra, but it produces something that really lives over A in a canonical way. And absolute prismatic cohomology, just to contrast this maybe. This is defined similarly, but without the A. So there you really just take the site consisting of all prisms B together with a map from R to B mod J. And what I'm also skimming over a little bit here is that the theory you get this way, if you write it down as a limit, is not perfectly well behaved, and you need to combine this with some non-abelian derived construction in full generality. But we won't need that today. Right. So let me give you an example. Just like it's a trivial example, but this maybe gives you some feeling for what this is supposed to accomplish. So if R is A mod I itself, then how does this limit look like? Well, in this case, you can actually check that there is an initial object in this relative prismatic site, which is given by B comma J just being A comma I. So prismatic cohomology of A mod I relative A simply gives you A. All right, so if you plug in A mod I itself, prismatic cohomology somehow lifts you back to A. And extending on this, there's this very useful formula in the Bad-Scholze paper on prismatic cohomology, where they introduce prismatic cohomology, which is the following. So more generally, right here I've told you about the case where R is just A mod I. More generally, let's look at the case where R is a further quotient of A mod I by a sequence of relations, and I want this to be a regular sequence. Then Bad Scholze give a formula for prismatic homology as something they call prismatic envelope. This again starts with A, but now you need to do some modifications that have to do with the fact that in this R you've killed more elements. And you would think that you need to quotient by stuff. But something cool happens. Somehow if you quotient on the level of the R, prismatic homology just gets bigger. And if you've ever done some computations with TP, you might have seen the same thing happen, that somehow if you make the ring smaller, then of course THH also somehow becomes smaller, but TP makes everything sort of as free as possible, and TP typically gets just more elements adjoined. And so what happens here is that you need to adjoin certain elements, R1 over D, R2 over D, and so on, where let's say D is a generator of our ideal. There's a similar formula, slightly more complicated, if I is not a principal ideal, but let's say we work in this principal case. So you adjoin fractions like this, but you adjoin them in the world of delta rings. So this is somehow another way to write this somehow a little bit more formally is this is the free delta ring over A on elements, let's call them maybe A1 to AN, mod relations like DAI minus RI. Right? Just like you would adjoin a fraction to a ring, you just have to do it in the world of delta rings. So if you add a generator, you're also adding like delta iterates of that generator. And if you add a relation, you're also adding delta iterates of that relation. And you actually have to complete this again. This is completion with respect to P and D. I find this very cool. That somehow you're making the ring smaller, you're adding more relations, but this prismatic homology, it just makes all the things you kill downstairs divisible by D, right? So somehow on the mod I reduction, they really become 0. But upstairs, you never forget anything. You're just making things divisible by this ideal I. Right. And so one crucial observation that you can make if you stare at this if you have some example like delta ring A and two elements that are both distinguished, and you consider R equals A mod R1 and R2, then if I have two different distinguished elements, this gives me two different ways to consider A as a prism, right? I could take the ideal generated by D1 or the ideal generated, sorry, this is D1, D2. I could take either of those to define the prism structure. So I get two things that are a priori different. I could take prismatic cohomology relative to one prism structure and prismatic cohomology with respect relative to the other prism structure. And one of these is going to look like A, where I've delta ring adjoint a fraction D2 over D1. And the other one is going to look like this, where I've adjoint D1 over D2. These look very different, But delta rings are kind of magical, and it turns out these just agree. And the reason for this is that if in a delta ring you have two distinguished elements, one a multiple of another, then U is automatically a unit. You can get that by applying delta and staring a little bit about what completeness gives you. So these two agree, and it looks like prismatic homology doesn't really depend on a prism structure on the base. And so we actually worked this out. It's kind of funny that that hasn't been observed yet, but it turns out prismatic homology is actually functorial not just in pairs of a prism and a ring over A mod I, but just in pairs of a delta ring A and any map of rings A to R. But in the case where the kernel of that map contains distinguished elements, it agrees with the thing that we've written down upstairs. And now comes the cool part. So this, we actually need this extended factoriality. This is not just some idle, we're generalizing things for the sake of generalizing. So what we actually want to write down is we want to write down some way to get absolute prismatic cohomology from relative prismatic cohomology, because relative prismatic cohomology in many cases can be described in terms of these prismatic envelopes. And if you've seen this paper by Liu and Wang that I referenced earlier, they do something like this on the level of THH, TP, and TC minus, where their trick is to describe the absolute thing as limit of some kind of co-simplicial resolution, where the degree 0 part is your work relative 1 variable, and then the degree 1 part is you just work relative 2 variables, and then the degree 3 part is you work relative 3 variables, and so on. And we can now, with this observation, do the same thing on the level of prismatic cohomology, because we know that it's factorial in maps of that don't respect the prism structure, right? If you didn't know that, then somehow, if I write this down, you first need to tell me what is actually the prism structure, right? So what I'm going to do here is I'm going to say, well, this R is something like OK mod pi to the n. So I want ZP considered as a prism via some Eisenstein polynomial, some minimal polynomial of pi. But then which prism structure would you take here? You could either take the Eisenstein polynomial in Z0 or in Z1 or something completely different. And it turns out to get prismatic homology, you don't need to make that choice. And so you get factoriality with respect to all the possible maps here. You get the full co-simplicial diagram. And so we prove this is a limit diagram. And all the terms here are actually envelopes, like I said above with this Bach-Scholze formula, right? This is really going to be something like Z P adjoint Z, and then delta ring adjoint Z to the N over E of Z. And this guy, this next guy is going to be something like, I again adjoin something like Z0 to the N E Z0, but then I also need to adjoin Z0 minus Z1 over E0, and I get this description from kind of arbitrarily picking a prism structure and then observing that I can write R by quotienting by Z0 minus Z1 by the Eisenstein polynomial and by Z0 to the N. and so on. So all of these are now ordinary rings described by some generators and relations description, and the limit is this prismatic cohomology. And well, then we actually produce some explicit generator and relations descriptions, and we really can compute that somehow this whole cosimplicial diagram has cohomological dimension 1 in a sense. So if you take the total complex, it's going to be the same as if you just replace this term by the kernel of the next map and the remaining ones by 0. So this really writes this guy as just the fiber of a single map, or like a two-term chain complex. So this is prismatic cohomology, and then to get TC, there's an additional map involved. I haven't said this in the beginning, but some of this TC comes from TC minus and TP as the fiber of another map. So what we get in the end is we get a square, right? So our original square arises from this via passing to TC, which is the fiber of a map from TC minus to TP. And on the level of prismatic cohomology, this corresponds to, well, I haven't talked about the Nygaard filtration, but these groups, like the associated gradient of TC actually relates to something called the Nygaard filtration on prismatic cohomology. And so there's a similar map like this on the level of prismatic cohomology. Actually with some twists. Let me maybe add these here without saying too much about them. But what we actually care about is this fiber. That's the thing that's the associated gradient of TC. And so in our square, let me maybe write this out once in full. Well, let me maybe write this out once just so I've written it down. Something's weird. CP adjoint Z. Right, this is relative prismatic cohomology with this Nygaard, like this Nygaard filtered part. That's the thing that corresponds to TC minus. And then there's this vertical map that corresponds to passing to TC, or these things called symptomic complexes that Ben might have mentioned. And then this is relative, so there's a horizontal map that somehow, that's this two-term chain complex that I mentioned above that somehow comes from this descent, from this cosimplicial diagram. So let me just write these maps, maybe these terms maybe as kernel. They're the kernel of the next differential in this cosimplicial diagram. We have some other weird name for them, but this is how this square arises. And now I want to tell you one more thing in the last 3 minutes, which is these things are, of course, I mean, these things, as I told you now, are somehow things we can understand in terms of generators and relations descriptions, but they're still hugely infinite. In the beginning, I've told you we have these finite squares. So where does that come from? Well, here's the last crucial ingredient that we use, which is that on these prismatic envelopes, we can define a filtration that comes from the z-adic filtration, basically, and then you give terms such as this Zn over Ez. You also give that filtration n. So we have this filtration on there, and then one thing we can do is we can analyze the associated gradient of that filtration. And what we can prove is that above this degree, so this additional filtration, we call that F. So on the graded F K for K bigger equal IN, this square has trivial cohomology. That's something we can prove by analyzing how this filtration interacts with this explicit generators and relations description. And so we can truncate the square, all the terms in it, with respect to the, let's maybe call it z-adic filtration, although it's somehow a refinement of that, with respect to the z-adic filtration. And it turns out those are then actually finitely generated. So out of this huge infinite list of generators that you get by considering these as free delta rings, actually only finitely many matter up to this filtration. And we have an abstract argument that shows that above that filtration, stuff doesn't matter. And well, then we just tell a computer how to work with these basis elements, and we can compute things. Right. Yeah, let me maybe finish here.
Great. Let's thank Achim for the very interesting talk. Any questions?
Yeah. So you mentioned at the beginning that there was this, when I was really large, the even K groups start to go away. How large is large in that kind of description?
Right. So I didn't really get to talk about that for time reasons. Sorry about that. But it turns out the bound that we get from our argument is exponential. So if you work with like z mod p to the n, then the I needs to be bigger, something like, I'm going to mess it up, but something like p squared over p minus 1 squared times p to the n, something like that. So it's going to be exponential in the n. And that looked really bad to us until we forced our computer to compute like z mod 8 and z mod 16 and z mod 32 for a large enough range. And you actually get a very nice exponential pattern as well. It's somehow by a factor of, at p equals 2, it's by a factor of 8 or so better than what we can prove. And the argument I use is really non-optimal. Like, it's clear that you can squeeze out some little better bounds if you just work harder. But it seems to me that the optimal bound might actually be exponential. So let me maybe, I'm not sure if Ben has shown you tables. I can show you one table to illustrate what I mean by this. So to share on my computer, let me do that very quickly. So I have these tables here. Can you see these?
Yeah.
So every column is one ring, and this is all p equals 2. The first column here is z mod 4, the second is z mod 8, z mod 16, and so on. And then I've just written the orders of the cyclic summons. And so, and 0 if there's no cyclic summoned. And so what you see here, the first K group where it starts to vanish for z mod 4 is degree 4. And then for z mod 8, it's degree 6. For z mod 16, it's degree 10. And then for z mod 32, it's degree 18. And it becomes a little bit more striking if you look at the last even degree K group, which is non-zero, because then that's in degree 2, 4, 8, and 16. So it does actually look like for p equals 2, the optimal bound is actually precisely exponential. I just have no idea how to prove that. The bound I can prove is somehow 8 times larger than that.
Compared to exponential, that's nothing. Any other questions?
I had a quick one about, so you told us where to find the square you started with in the prismatic cohomology. One of the striking things about the theorem was that all of the corners of the square were the same rank, and that's not at all clear from the description you gave. Is it possible to say why they turn out to all be the same rank?
Right. So I guess it's not just that they're the same rank. It actually turns out that all the maps in the square are rationally isomorphisms. So conceptually, like a better way to say this conceptually would be that the fibers of these various maps happen to just be torsion. And so, for example, this means that the absolute TP of these rings happens to be torsion. So I'm not sure I can prove that without, like that's the statement that the horizontal maps are rational isomorphisms. Not sure I can prove that without this square. I haven't thought about that too much, but I think that seems to be the conceptual statement here, that somehow both the relative version of TC and the absolute version of TP seem to be torsion in this setting.
Very cool. Thank you.
Other questions? I have a short question regarding what kind of software did you write your code in? Did you use any particular software? Right.
So currently we're doing this in Sage, just because it was the easiest thing to get off the ground with, right? Like it has all these things built in, like you have like the p-adics, all kinds of stuff with multivariate polynomials and so on. But I guess we are running into some performance bottlenecks due to the fact that the way Sage handles multivariate polynomials is not precisely the thing we need. Like we need stuff only up to some filtration, and Sage is, I guess, not built for that kind of application with like at the forefront. So we're thinking about writing this, maybe like writing parts of this maybe by hand just in Python. But so far it's all some Sage notebook.
All right, other questions? Oh, then let's thank Achim for this very interesting talk.
Thanks.
Thank you so much, Achim, for coming virtually to us and giving the second half of the talk to show us the real computations. Thank you very much. We appreciate that. So
yeah, it was fun. Thanks.
Okay. With that, I finish the Zoom session. Thanks, everybody.